At August Breweiler AG, the production of engineered wood components follows a precisely controlled and vertically integrated process designed to ensure maximum material utilization, structural integrity, and aesthetic quality. The production begins at the Balterswil sawmill, where harvested logs primarily sourced from sustainably managed Swiss forests are delivered and sorted. Each log is measured, scanned, and visually inspected for straightness, knot distribution, and internal flaws. Optimized cutting patterns are calculated using software-guided algorithms to minimize waste and extract boards of the highest yield and quality. Logs are then debarked and sawn into dimensional lumber using bandsaws and circular saw systems, producing rough-sawn planks for further refinement. Moisture sensors monitor internal wood conditions in real time. Once target values are achieved, the material is transported to the Fimmelsburg glue lamination facility. At this stage, boards are planed, defects are removed by cross-cutting, and finger joints are applied to achieve longer structural members. High-strength, formaldehyde-free resins are applied between lamellae, and the assemblies are pressed under high pressure in multi-layer hydraulic presses, forming beams and panels of consistent density and bonding performance. These products meet EN 14080 standards for load-bearing structural timber. Once sawn, the lumber is stacked and dried in computer-controlled kilns. These drying chambers follow specific temperature and humidity cycles, depending on species and board thickness, reducing moisture content to between 8% and 12%, a critical threshold for structural applications and glue bonding. The laminated elements then enter the Hobach work, or planing mill, where advanced four-sided planers shape them to exact final dimensions. Surface quality is carefully monitored with inline laser scanning and high-speed cameras that detect micro-defects, knots, or surface inconsistencies. Moisture content is rechecked, and boards outside tolerance are automatically rejected or rerouted for rework. Elements designated for visible architectural use are polished to achieve surface classes defined in DIN 18334, ensuring suitability for exposed installations. Following planing, the wood enters Lacquer Work 1, the first coating facility. Here, a base coating is applied either through vacuum impregnation, flow coating, or spraying, depending on the required protection level and final application. Treatments include biocides, insecticides, and water-repellent primers that increase durability and resistance to environmental exposure. The coatings are cured in drying tunnels, featuring a combination of infrared radiation and convection heating, optimized for both solvent and water-based systems. Adhesion and penetration depth are tested per ISO 2808 and EN 927 standards. The final phase occurs at Lacquer Work 2, where surface finishing takes place. Top coats, including weather-resistant UV blocking lacquers, breathable acrylic films, or pigmented polyurethanes, are precisely applied via electrostatic sprayers or curtain coaters. Every component passes through a finishing line that includes forced air curing ovens and quality control stations. Surface resistance, gloss level, and color matching are verified using spectrophotometers and abrasion testing equipment in accordance with RAL and ISO standards. Each batch is logged, traceable, and certified. This end-to-end production chain ensures that every wooden product from August Breweiler AG meets the highest standards for structural performance, visual consistency, and long-term durability, while also adhering to environmental and regulatory best practices. At Bloomer Lehman's Timber Industry Division, roundwood is processed into high-quality timber products through a precise and controlled workflow. The process begins with selecting Swiss round logs, followed by debarking, cutting, and drying under optimal conditions. Depending on the final application, lamellas are then prepared and laminated into beams or panels. Advanced CNC machinery is used for milling and shaping components to meet exact specifications. These elements are utilized in various architectural and structural applications, particularly in free-form timber constructions. The integration of traditional craftsmanship with modern automation ensures both efficiency and outstanding surface quality. Gump and Meyer has significantly increased its production capacity by installing a new automated production line for the production of Technowood door frames, which has doubled its production efficiency. The state-of-the-art line incorporates advanced machinery and process controls designed to deliver high precision and efficiency throughout the entire production process. The production process begins with the selection of high-quality engineered wood panels, ensuring consistent material properties suitable for doorframe applications. The panels are automatically cut using CNC machines, which precisely shape the individual components of the doorframe, including the vertical bars, rails, and posts. CNC technology ensures precise dimensions and clean cuts, minimizing waste and ensuring repeatability. After cutting, the components are transferred to the assembly station, where they are joined using semi-automatic cutting using advanced joining techniques. The assembly system includes automatic latches or biscuit joints, which enhance mechanical stability. Then, an automatic machine trims the inner wood edge to prepare the door for installation. After assembly, the doorframe undergoes finishing operations, including sanding and surface treatment. Surface finishing improves both aesthetics and durability, protecting the wood from moisture and wear. Throughout the production process, integrated quality control systems continuously monitor key parameters such as dimensions, joint integrity, and surface finish. This new automated line not only increases productivity, but also improves product consistency, quality, and overall production efficiency, positioning Gump and Meyer as a leader in the production of precision-engineered wooden door frames. Wisdom Stockholm is a complex timber-grade shell structure composed of free-form, double-curved glulam elements. Each component was uniquely shaped using parametric design and CNC fabrication to ensure precise geometry. Hidden steel connectors allowed structural integrity without visual interruption. The timber elements were prefabricated off-site, then bent and twisted into final form during installation, an unprecedented technique in this context. Bloomer Leman coordinated design, production, and erection, ensuring high accuracy and efficient assembly. The project demonstrates how engineered timber, advanced digital planning, and integrated workflows can deliver a structurally efficient and architecturally iconic free-form building. In July 2017, the final free-form timber element for the Swatch headquarters was precisely machined on the Technowood TW mill. The 5-axis CNC system enabled high-accuracy shaping of complex geometries, ensuring each unique glulam component met the exact specifications for seamless structural integration. Modern planing machines operated by experienced technicians ensure the high quality of visible timber surfaces. These machines are essential for achieving smooth, precise finishes and are used across a wide range of products, including structural elements, cladding panels, and custom architectural components in timber construction. Leman produces high-quality finger-jointed timber products, including KV battens, boards, and raw planed wood, in standard or custom lengths at its in-house finger jointing facility. Utilizing advanced scanning and planing technology, the company ensures highly efficient, precise, and dimensionally accurate processing for superior performance in downstream timber applications. For the new 4-story psychotherapy facility at Thurgau Hospital in Münsterlingen, Leman produced 550 square meters of roof elements, 1,100 square meters of floor and ceiling panels, 2,650 square meters of interior walls, and 1,000 square meters of exterior wall components. Using advanced 3D modeling and CNC-controlled production, all elements were prefabricated with high-dimensional accuracy and quality. Gump and Meyer GmbH employs a highly automated production line focused on CNC machining combined with specialized lifting systems. Their 5-axis CNC machines are precisely programmed to perform cutting, drilling, groove milling, and surface finishing on large timber frames within a single cycle, ensuring consistent quality and tight tolerances. Notably, the integrated lifting system with suspension mechanisms and automated stacking cranes enables safe and efficient handling of large wood panels without manual intervention, ensuring accurate positioning and operator safety. The entire production process, from material preparation and machining to preliminary assembly, is synchronized through centralized production management software. This solution delivers high efficiency, minimizes errors, reduces production time, and is well suited for large-scale modular manufacturing in modern industrial timber construction projects. Our manufacturing process begins with precise 3D scanning of the construction site to create accurate digital models. These data are transferred into CAD software to design perfectly fitting components. Next, CNC-controlled machining is performed on the materials, ensuring the highest accuracy and quality. The prefabricated elements are then transported to the site for efficient assembly. This workflow enables fast, error-free construction, from the initial digital scan to the completed building. The rhomboid cladding LERHO features a separate starter piece, integrated profile grooves for facade slats, stabilizing hold tabs, and a snap-fit mechanism. A single screw enables fast installation and clean aesthetics. The production process for the timber modular structure at Rosenmar School in Cologne begins with selecting high-quality wood, which is carefully dried and treated to ensure durability and stability. The wood is then precisely cut and processed using advanced CNC technology according to the design specifications of each module. Components are assembled in a controlled factory environment, integrating electrical, plumbing, and insulation systems to streamline on-site construction. Strict quality control checks are conducted throughout the process to guarantee accuracy and safety. Once completed, the modular units are transported to the site and quickly installed, providing modern, functional learning spaces for 180 students, creative learning spaces, and comfortable classrooms. Leman produced 45 timber modules for the Lattice project in St. Gallen, using precision-controlled modular construction methods. Each module was prefabricated in the company's specialized facility, involving CNC milling, framing, insulation, and interior finishing under controlled conditions. This ensured consistent quality, dimensional accuracy, and efficient logistics. The modules were then transported and installed on-site within a short time frame, demonstrating the technical advantages of timber modular construction for flexible, sustainable, and rapid urban development projects. A site visit provides valuable insights into the assembly of prefabricated components. On-site, elements are precisely and efficiently installed using advanced lifting equipment and well-coordinated workflows. The integration of multiple trades ensures seamless construction progress and adherence to project timelines. This combination of meticulous digital planning, accurate off-site fabrication, and professional on-site execution guarantees timely project completion, structural integrity, and high-quality workmanship directly at the construction site, even under challenging logistical or environmental conditions. Each roundwood house is meticulously handcrafted, using high-quality Corinthian fir or spruce logs, ensuring a unique structure tailored to the natural characteristics of the timber. The production process begins at the company site in Hobach, located in the Corinthian Draughtal region, where skilled craftsmen carefully select each log based on its size, shape, and structural integrity. The construction technique draws from Canadian log building methods developed since the 1970s, which focus on precision fitting of logs to create airtight, stable building envelopes. To achieve this, the craftsmen first perform a full trial assembly of the house on site. This process involves positioning each log exactly where it will be installed, then disassembling the structure for detailed shaping and fitting. Using a specialized marking tool known as a scriber, the craftsmen transfer the natural unevenness of the lower log onto the upper log to define the contact surfaces accurately. This marking guides the manual milling and carving operations to form tight, form-locked joints, especially the longitudinal channels that are essential for the structural stability and thermal performance of the building. Due to natural wood properties such as shrinkage and moisture loss, the logs undergo slight dimensional changes after assembly. The design anticipates these changes by allowing deliberate small gaps during construction, which close over time as the wood settles, ensuring long-term airtightness. The entire assembly process demands precise coordination among the craftsmen, who rely heavily on experience and communication to maintain safety and quality standards. This artisanal approach, combined with modern precision tools and a deep understanding of wood behavior, results in sustainable, durable, and energy-efficient roundwood houses that adapt to their environment while providing comfortable living spaces. The construction and installation of the bulk material silo system for the city of Gosau involved a comprehensive process managed by Leman, specializing in silo and plant construction. The project began with the demolition of the existing silo facility, ensuring safe and efficient removal of the old structure to prepare the site for new construction. Following demolition, foundation reinforcement work was carried out to guarantee a stable and durable base capable of supporting the new silo system's significant loads. This included the installation of reinforced concrete footings and substructures designed to meet stringent engineering requirements. Simultaneously, components for the silo system were manufactured at the Leman production facility, where precise fabrication processes ensured high-quality parts built to specification. These included steel panels, structural supports, and mechanical elements essential for the silo's operation. Concrete works were performed on-site, encompassing the pouring and curing of foundation slabs and support structures, executed with strict adherence to engineering tolerances and quality standards. Finally, the assembly and mounting phase involved on-site installation of all prefabricated components, followed by thorough alignment and integration of mechanical and electrical systems. The project was completed with rigorous quality checks, ensuring full operational functionality and compliance with all safety regulations. The Kehrer House, realized by Hobach Holtzbau, exemplifies advanced timber construction using the Holtz standard Bauweise timber frame construction method, paired with traditional carpentry joinery techniques. This system involves a load-bearing framework of vertical timber studs and horizontal beams, typically manufactured from kiln-dried softwoods, such as spruce or fir. The timber elements are cut to precise dimensions and assembled in controlled factory conditions to ensure dimensional accuracy and tight joinery tolerances. The construction begins with foundation work on site, where anchor bolts and connection plates are positioned to receive the prefabricated wall elements. The wall panels are then delivered as fully assembled units, each composed of structural framing, sheathing panels, often OSB or fiberboard, insulation cavities, and weatherproof membranes. Using crane support and predefined erection sequences, the panels are installed in succession to form the external and internal walls. One hallmark of Hobach Holtzbau's approach is the use of traditional timber joinery, such as mortise and tenon joints, wooden pegs, dowels, and scarf joints, instead of relying exclusively on metal fasteners. These joints are crafted using CNC machining centers for high precision and are further refined by hand to ensure optimal load transfer and structural cohesion. The roof trusses follow similar joinery principles and are hoisted into position once the wall assemblies are secured and squared. Open windows are published in the wall panels to ensure standard dimensions. When erecting the walls, the frame windows are attached to the windows with a system of adjustment supports and common screws. Gaps around the window frames to let in steam and wind. You can't wait to see what you're looking for. The roofing step is done after the roof system is complete and the insulation has been installed. Before that, the underlayment is spread evenly over the frame system, ensuring water resistance and reducing moisture. Next is the shingle frame system to raise the tile layer. Tiles are selected according to technical and aesthetic requirements, then slid from bottom to top, ensuring that the tile products are tightly interwoven and firmly secured with specialized chains or hooks. The manual tiling is standard in terms of slope, spacing, and tries to ensure the ability to drain rainwater and withstand wind loads according to Eurocode standards. Finish the exterior surfaces with protective layers of wood or decorative cladding materials, and check the overall construction from stable configuration, airtightness, and insulation efficiency according to technical standards. This process combines traditional manual techniques and modern machinery, creating a solid, durable wooden frame house that meets both technical and aesthetic requirements, while optimizing energy efficiency and no need for scanners. Behind the scenes in the production hall, 20 double-curved timber roof beams, totaling 200 meters in length, were manufactured. The largest component weighs 2 tons and has a volume of 4.35 cubic meters, highlighting precision in large-scale timber fabrication. In the 2019 Grill Pool Challenge, Leman implemented a technically precise and well-coordinated workflow to create a custom timber installation. The structure consisted of prefabricated wood modules engineered and cut using CNC technology in the company's production facility. CAD-based planning ensured millimeter-accurate fits, while surface treatment and structural reinforcement were applied prior to delivery. The prefabricated components, including load-bearing timber frames and deck panels, were assembled on-site using concealed connectors and rapid mounting systems. This temporary yet structurally sound installation The production cycle began at the Erlenhof facility, where locally sourced Swiss roundwood was processed. Logs were sawn into lamellas, kiln-dried, and re-laminated using custom curved forms to achieve the required geometries for freeform construction. The construction of the Swatch headquarters in Biel represents one of the most advanced applications of freeform timber engineering, executed by Leman with sub-millimetric precision. Designed by renowned Japanese architect Shigeru Ban, the building features an organically flowing timber structure consisting of over 4,600 unique elements, making it the largest timber office building in Switzerland and the largest single timber structure ever implemented by the company. These glued, laminated timber (GLT) components were then milled using multi-axis CNC machines. Each beam underwent detailed shaping, fixture mounting, surface finishing, and individual quality inspection before packaging and shipment. The accuracy of CNC milling ensured that all geometry-driven constraints were respected within a tolerance of plus or minus 0.5 millimeters. To manage the high variability of part geometries, a fully parametric design model was employed. Initial 2D architectural plans were translated into a 3D parametric dataset by design to production, allowing designers to encode rules and constraints that could be automatically reapplied across the complex form. Parametric detailing made it possible to define joint locations, bolt spacings, and connector tolerances in relation to local geometrical anchors, thereby enabling automation of repetitive construction logic despite unique shapes. Given the limitations in machine capacity, Leman utilized 7 CNC machines simultaneously. This demanded a tightly controlled digital workflow. Exact part IDs, machining instructions, and time-coordinated production schedules had to be synchronized across all systems. Custom in-house monitoring tools were developed to track machine throughput, detect bottlenecks, and ensure continuous data validation. The on-site erection phase, lasting over 10 months, was divided into 13 installation stages. Falsework scaffolding was used to support curved beam segments during assembly. Using high-precision tachymeters, the team ensured correct alignment in all 3 axes. Assembly followed a just-in-time sequencing model, as each part had to be placed immediately at its designed position. No deferral or reordering was possible due to the interdependent structure. Each beam, delivered in its final state, was handled using gloves to prevent soiling, with tolerances across the entire shell kept within plus or minus 5 millimeters. Upon closing the final ridge beam, the structure self-stabilized and the temporary scaffolding was removed. This project showcases a holistic integration of architecture, computational design, fabrication, and construction logistics, pushing the limits of timber construction to new heights. The first step begins with the harvesting and transportation of raw stem wood. The raw material typically consists of mixed species and sizes of stem wood, which must be efficiently handled and prepared for chipping. At the collection site or processing yard, the logs are sorted and fed into the chipping machinery. The processing of mixed stem wood into wood chips is a multi-stage operation involving heavy-duty machinery, primarily from manufacturers such as Fendt, Hobach, and John Deere. This process is critical in the production of biomass fuel, wood-based panels, and other industrial applications where uniform wood chips are required. Fendt tractors, known for their high torque and robust performance, are commonly employed to maneuver and position large volumes of logs. Equipped with powerful hydraulic systems and durable chassis, Fendt tractors facilitate the loading of stem wood onto conveyors or into feed hoppers of chippers. The Hobach wood chippers are specialized machines designed for efficient and consistent size reduction of wood material. These chippers employ high-speed rotating drums or disc blades that shear the stem wood into chips of uniform size. The feed system is typically equipped with heavy-duty rollers that ensure a steady and controlled input of logs into the cutting chamber, preventing blockages and optimizing throughput. John Deere machinery, often used for additional wood handling and forwarding, supports the chipping process by transporting wood from forest sites to processing locations. These machines feature tractor or wheeled chassis for mobility over rough terrain and high-capacity loaders for handling bulky timber. During chipping, quality control measures are vital to ensure the wood chips meet required specifications. Parameters such as chip size, moisture content, and contamination levels are monitored. The moisture content affects combustion efficiency in biomass applications, while size uniformity impacts downstream processing. After chipping, the wood chips are conveyed to storage areas or directly loaded onto transport vehicles for delivery to biomass power plants or industrial consumers. The entire operation requires synchronization between machines and operators to maintain continuous workflow and minimize downtime. Maintenance of the cutting tools and mechanical components is essential for consistent chip quality and machine longevity. Regular sharpening of blades, lubrication of bearings, and inspection of feed rollers prevent unexpected failures. In summary, the integration of Fendt tractors, Hobach chippers, and John Deere forestry machinery enables an efficient and technically sound process of converting mixed stem wood into high-quality wood chips. This process supports sustainable biomass energy production and contributes to effective forest resource utilization. Naegeli Holtzbau is a renowned expert in timber construction, employing a highly technical, integrated process that ensures precision, efficiency, and sustainability at every stage. The company combines traditional craftsmanship with cutting-edge machinery and digital technology to produce high-quality timber components and assemblies. The initial stage begins in the forest, where carefully selected trees are harvested based on species, growth conditions, and mechanical properties suitable for structural use. Commonly used wood species include spruce, pine, and fir, chosen for their strength-to-weight ratio and workability. The production workflow involves several key phases: timber harvesting and sawmilling, delivery and cutting to size, automated drilling and doweling, CNC machining, structural assembly, interior and exterior finishing, and final inspection and handover. Each phase incorporates strict quality control and optimization to deliver structures that meet demanding architectural and engineering specifications. Post-harvest, logs are transported to the sawmill, where the transformation from raw material to structural timber begins. The logs undergo debarking to remove the outer bark layer, which is crucial for ensuring a clean surface for subsequent machining and treatment. The logs are then precisely cut into standardized dimensions using computer-controlled bandsaws and circular saws. The sawmill employs advanced sawing optimization software to maximize yield, minimizing waste by determining the best cutting patterns based on log diameter and quality zones. This technology also ensures that beams and boards have uniform thickness and length, critical for further processing. Moisture content control is vital at this stage. The freshly cut timber typically contains 30 to 60% moisture, which must be reduced to approximately 12 to 15% through kiln drying. Kiln drying is carefully monitored to prevent defects such as warping, cracking, or fungal growth. Proper moisture content enhances dimensional stability and bonding performance in later assembly. After drying and initial sawing, the timber components are transported to the production facility's processing lines. The logistics are carefully planned to maintain the sequence of components for efficient workflow downstream. At the cutting station, high-precision CNC cutting systems are employed. These multi-axis saws execute cuts with millimeter accuracy, producing complex shapes and joints required for timber frame construction. The CNC systems are programmed from BIM, Building Information Modeling data, or CA drawings, ensuring exact compliance with architectural plans. Automated cutting allows simultaneous processing of multiple parts, reducing cycle times and increasing throughput. The machines can also perform bevel cuts, notches, and dados, facilitating mechanical interlocking in the assembly phase. The CNC cutting step also optimizes material usage by nesting parts tightly on larger boards to reduce scrap. One of the defining features of Naegeli Holtzbau's production line is the automated drilling and doweling process. This stage replaces traditional metal fasteners with precision-engineered wooden dowels, enabling strong, durable, and aesthetically pleasing joints. The multi-axis CNC drilling centers are capable of performing simultaneous hole drilling with exact depth and diameter controls. Holes are drilled at predetermined positions for dowel insertion, allowing exact alignment of timber elements during assembly. The drilling programs are generated from 3D models, ensuring perfect fit for complex joint geometries, including mortise and tenon, lap joints, and cross-dowel connections. The automated dowel inserters then place hardwood dowels into the drilled holes with pneumatic or hydraulic pressure, ensuring tight, stable joints without gaps. This doweling method improves sustainability by reducing reliance on metal fasteners, facilitating easier recycling of timber components, and preventing corrosion-related structural issues. The process also speeds up assembly on-site, as components fit precisely without the need for manual adjustment or additional connectors. Following drilling and doweling, the timber elements proceed to CNC milling machines for additional profiling. This step enhances the dimensional accuracy and surface quality of parts, while adding functional and decorative features. High-speed milling heads with diamond or carbide tools perform operations such as groove cutting for insulation channels, tongue and groove joint formation, surface smoothing, and shaping of architectural profiles. The CNC machines operate under computer numerical control, executing complex toolpaths based on CAD designs to achieve tolerances within 0.1 millimeters. This level of precision machining enables modular construction approaches where components are prefabricated to exact standards, facilitating rapid and error-free assembly on-site. Surface finishes at this stage are optimized to minimize sanding labor later and improve adhesion for coatings or veneers. Advanced software tools monitor tool wear and compensate tool path deviations to maintain consistent machining quality throughout production runs. Automated dust extraction systems integrated into the CNC centers ensure a clean working environment and protect the machinery. After machining, the timber components are delivered to the construction site or assembly hall. Naegeli Holtzbau employs state-of-the-art laser-guided positioning systems and 3D scanning technologies to guarantee structural accuracy during erection. Assembly begins with the placement of foundational beams and vertical posts according to the structural design. The use of prefabricated dowel joints allows rapid and secure connections, drastically reducing on-site labor and time. Precision instruments continuously monitor verticality, squareness, and alignment to ensure compliance with engineering specifications. Adjustments are made using hydraulic jacks or shims where necessary to maintain the structural envelope within tolerances. This phase requires coordination between structural engineers, carpenters, and site supervisors to ensure seamless integration with other building systems such as foundations, utilities, and facades. Once the primary structure is erected, finishing work proceeds on both interior and exterior surfaces. Internally, insulation materials such as mineral wool or cellulose are installed within the timber frame cavities to meet thermal and acoustic standards. Timber surfaces undergo sanding and treatment with protective oils, stains, or varnishes, selected for durability, fire resistance, and aesthetic preferences. Surface treatments also provide moisture repellency and UV protection to extend service life. Exterior finishing includes application of weather-resistant cladding materials, wood siding, fiber cement panels, or metal sheets, depending on architectural design and local climatic conditions. Vapor barriers and waterproof membranes are installed to prevent moisture ingress and maintain airtightness. Windows, doors, and other building components are integrated with precision to maintain thermal performance and prevent thermal bridging. The final step involves thorough inspections encompassing structural integrity, joint quality, surface finish, airtightness, and energy efficiency performance. Quality assurance personnel utilize non-destructive testing methods, including laser scanning and moisture meters, to verify compliance. Any deviations or defects identified are rectified promptly, ensuring the delivered structure meets contractual and regulatory requirements. Upon completion, detailed documentation, including construction drawings, material certificates, and maintenance guidelines, is handed over to the client. Naegeli Holtzbau also provides post-occupancy support, ensuring long-term performance and client satisfaction. Naegeli Holtzbau exemplifies an advanced, technically rigorous approach to timber construction that integrates precision manufacturing, automation, and digital design. The workflow from forest to finished building is tightly controlled to maximize material utilization, dimensional accuracy, and structural performance. Automated drilling and doweling combined with CNC machining facilitate modular construction with superior quality and sustainability. Their expertise and technology enable the efficient delivery of complex timber structures that fulfill modern architectural and environmental demands. Every day, large volumes of fresh wood chips are produced as a byproduct in OLWO sawmills. A portion of these high-quality residual wood materials is supplied to Gutex, where they are transformed into ecological wood fiber insulation boards within a closed-loop, sustainable production cycle. The process begins with responsibly managed Swiss forests, where selective harvesting and gentle forestry practices ensure the health of the ecosystem and the quality of the raw material. After debarking and primary sawing, OLWO generates clean, fresh wood residues that serve as ideal input for insulation production. These chips are efficiently transported to the Gutex facility, where they undergo several processing steps, including defibration and drying. The result is a range of dimensionally stable yet flexible insulation boards with excellent thermal storage capacity, effective sound insulation, and a strong environmental profile. Each step in the production chain is carefully documented to meet strict environmental and quality standards. Insulation boards made from OLWO chips are long-lasting, recyclable, and capable of storing carbon dioxide, thereby making a meaningful contribution to sustainable construction practices. This efficient use of regional raw materials promotes climate-friendly, resource-conscious building methods and supports a circular economy.